Okay, virtual camera, Discord. Let's see, make sure the audio is going since I had that one problem that one time. Listening to London Symphony Orchestra. All right. All right, so that's going. Good to go. So this is going to be a bit of a weird class. We've got people out. We've got not very many people in. We've got people joining virtually. So I may end up just picking a few problems at some point that I think look hard if we don't get enough questions in person and through Discord. And we probably will still get out early. So we will see. So see what happens. At least it's not pre-cal, where I just would teach to an empty room for a few minutes if nobody was here. All right, let's see. We're at 4, what? We're almost to a test, right? We're at 4.6 or 4.7? Yeah, isosceles and equilateral, that's right. Did we do them both? Just 4.6. Why you mean mugging me? Oh, goodness. What a sneeze. Okay. All right, what did we do? 10 through 24. 2 through 24. Number 2 is segment E and segment EA and segment EC. Number 4 is 60 degrees. Number 6 is 16. 8 is a proof. We can do it assuming we need to in a minute. Well, we may do both of the proofs. Number 10 is segment AB and segment AF. Number 12 is segment AD and segment DE. Number 14 is angle AFH and angle AHF. 16 is 65 degrees. 18 is 3, 20, x equals 3. 22, x equals 1.4, y equals -1, and 24 is another proof. So do you have questions that are not ones that are the proof? We may need to do 1 or 2 of them regardless. Gavin, are you here yet? All right, good. I'm glad you're here. $14, sure. Actually 12. Okay, same picture either way. So, let's see. Didn't I just grab? Oh, I guess I didn't. All this wind's got my allergies going crazy. Got this crazy looking pentagon shape. Aliens. Okay, so you said 12. Refer the figure at the right. All right, so if angle DAE is congruent to angle DEA, name 2 congruent segments. So Angle DAE, right? DAE, so that's this one, right? If DAE is congruent to DEA, so if these are congruent, then name two congruent segments. So those, we're talking about isosceles triangles and equilateral triangles, right? So it's going to have something to do with those, pretty certainly. What is true about isosceles triangles? Gavin, you can answer too. You're in class. Not the whole thing. So, no, not quite. It says that in an isosceles triangle, the base angles are congruent, right? So in an isosceles, and if the two base angles are congruent, then the triangle is isosceles, right? Yeah, peak. So that means that triangle ADE is what kind of triangle? It's isosceles. So what is that? So where are their congruent segments if these are the base angles? No, it's not EA, that is the base, right? It's turned sideways because the base is up here in the air. He's tilted over sideways, right? Yeah, so it's AD and ED. So AD, D is congruent to DE. Oh, failure. All right. Gavin, what other questions do you have that are not the proof yet? We'll probably do both proofs today.
Can we do number 2?
Number 2, sure. I'll leave that picture in case we have to go back to it. Number 2 has got a picture that looks like this. And it says if angle EAC is congruent to angle ECA, name two congruent segments. So EAC, so that's inside, right? That's this little triangle. EAC is congruent to ECA. So those two are congruent. So which triangle, Gavin, is isosceles because of those two angles? Okay. Which triangle is congruent because these two base angles are congruent? So EB is just this segment. Which triangle? There are two triangles. There's this triangle, the ABC, and then the AEC. So which one is isosceles because of that on this question? Did you say EB? Okay, ABC, so ABC is the big one, but we know on number 2 it gives us EAC. So is E in the big triangle or the little triangle? The smaller one. So the smaller one is congruent. So that tells us something about these sides. So for this, AE is congruent to CE. All right? What else, boys? What? 24. Is that the proof? Sure. And 8, which is also the proof. Yeah, we'll start with 24. Sounds good. Did you try them? Good. All right. Picture looks like this. And we are given that x, y is congruent to xz, and w is the midpoint of xy, and q is the midpoint of xz. And we're supposed to prove that WZ is congruent to QY. All right? So, let's label this one, start there, that XY, so that's this big one, is congruent to XZ. So that's congruent to that. Okay, so we're supposed to prove that WZ, so this guy, is congruent to this guy. That's where we're trying to get to. So if we can get some triangles that are congruent, we could get to CPCTC, or if we got some isosceles something, there's all kinds of different ways we could look at it. There is 2 parts of the given that we haven't used yet, so how could we use the given? Yes, the midpoint, with the fact that those are the midpoint, what does that tell us? Not QY. W is the midpoint of XY. What does that tell us? If this is the midpoint, what's true about these segments? They're congruent, yeah. So we could say that XW is congruent to WY, and that XQ is congruent to QZ. What lets us say that? Definition of midpoint, that's right. Great, so we have this is congruent to this, and we have this is congruent to this. Nice. What kind of triangle is that big triangle? It's what? A scalioid. Isosceles. Is that the word you're trying to say? Oh, well, I don't know what you're... Hey, try. Oh, no, it's not scalene. It's definitely not scalene because we said that this one is congruent to that one. So if two sides are congruent, then it's isosceles, right? Mm-mm. So we could say it's isosceles, right? Triangle X, Y, Z is isosceles because the definition of isosceles, great. What does that tell us about some of its angles? Which ones? Yeah, so you can't just say Y and Z, but yes, X, Y, Z and X, Z, Y. The base angles are congruent, right? Okay, so we can say that angle X, Y, Z is congruent to angle X, Z, Y. I'm not trying to be absolutely obnoxious, but we do know that class starts at 9, right?
I actually got pulled over.
Did you today?
Yeah.
Well, I'm sorry about that. Also, class starts at 9. It has the whole year. It will the rest of the year. Okay, so base angles of isosceles, right? Base. Did you get pulled over in this little road over here? I've done that once before too. Base angles of isosceles. Okay, so we just said that this is congruent to this. If we get one more bit, we could say that this triangle and this triangle are congruent, which would pretty much get us there, right? Because then we could CPCTC the rest. So if we're looking at this triangle and this triangle, a lot of scribbles on this one, right? If we look at those two triangles, we've got, oh no, we don't have sides, just kidding. Not yet. Not yet, we don't. Oh yeah, I remember this proof. Most of the proofs in this chapter are like 3 steps, and this one's like 12. It's great. So we don't yet have that WY is congruent to QZ, right? We need that. We can go ahead and say that this bottom one is congruent to itself, right? What's a property that says something is congruent to itself? Reflexive, yeah. So segment YZ is congruent to segment ZY because of reflexive. Okay, so we need to be able to get, we've got WY and we've got QZ, we've got them kind of here, we can add them up and do some other things and maybe do some segment addition and shenanigans and get there. We've got them here, so we can at some point use this because we want this one is congruent to this one, right? We've got them where they're just not congruent to each other yet. So those two big sides, what kind of relationship could we set up with segment addition? What does segment addition say? says we can add up the two little segments to get the big segment, right? So we can say that the measure of segment XW plus the measure of segment WY equals the measure of segment XY. We can go ahead and say the same thing on this side, right? The measure of segment XQ plus the measure of segment QZ equals the measure of segment XZ. True enough. And what lets us say that? Segment addition, yes. Right? Now what could we say? XY equals XZ, right? So we've got these down here, right? So we could do something with that. We've also got XW and XY and WY being equal. We've got XQ and QZ being equal. So we could do some, what is that called when we start replacing stuff? Substitution. Now we need to, these all say measures and these all say congruent, right? So we need to real quick shift that over. Oops. That the measure of XW XW equals the measure of WY, and we can say the measure of XQ, this is this one, equals the measure of QZ, and we can also say this one, the measure of XY equals the measure of XZ. What lets us say that since they're congruent, their measures are equal? All we did was turn this one, and this one into the measure of it equals the thing. That's all we did. What lets us say that? We didn't do substitution yet. We're about to. Definition of congruent segments is what we're looking for. On a problem like this, especially one with this many steps, if you didn't include this line, I probably wouldn't count off. But now we need to do some substitution, right? We want it in terms of WZ, so we want the WZ. We don't want it in terms of what WZ is where we're headed. We want it in terms of WY and QZ, right? Because those are then the triangles that we're interested in. So we need WY to stay there. So since XW equals WY, we can turn this into WY, right? Okay. So we can say the measure of WY plus the measure of WY equals the measure of XY. We'll leave that one the same. We'll change the other one. We also want it in terms of QZ because that's also the triangle we're interested in. So we can turn this into QZ because XQ equals QZ. right? So we can turn this measure of segment QZ plus the measure of segment QZ. And we can turn this one so that these two match. Where am I? XZ. XZ is the same as XY, so we could turn this one into XY, and then these two are going to match, which means we're going to be able to substitute some stuff in a minute, right? So we can turn this also into the measure of XY. What did we do there? We changed one thing into another. What's that called? Substitution. Easy peasy. Now this, remember that this is like, these are the same, right? So we've got x plus x equals something else. What can we do with those x's? 2x. We can do the same thing here. The measure of xy is just a really ugly x, right? So we can turn this into 2 times the measure of wy equals the measure of xy. And the same thing here. 2 times the measure of qz equals the measure of xy. What lets us do that? You could say substitution. You could also say combining like terms. I would accept that. That would be fine. In geometry, probably substitution is really the correct thing. But combining like terms, something like that would also be fine. Now what could we do? These are both equal to xy now, right? Because we substituted xy in for xz because they're congruent. All right, so these are both equal to xy, so what can we do with them? Pretty much, almost, we're getting close. What can we do? What can we do with this side and this side since they're equal to the same thing? They are equal. What property is that? You would think substitution, but stop and think for a minute, because this is actually the property that says if A equals B and B equals C, then A equals C. What property is that? It's your favorite. No, we're not there yet. We're going to get to SAS in a minute. No, it's the transitive property. So 2 times the measure of, that's a W, WY equals 2 times the measure of QZ, because of the transitive property. What can we do with those 2's? If it was 2x equals something, how could I get rid of the 2? Divide. Divide the 2 on both sides, and this equals this, right? So the measure of WY equals the measure of QZ. You can call it substitution, you can call it division property of equality, whatever. So WY now equals QZ. Their measures are equal, which means that WY is congruent to QZ. How did we turn the measure into the congruent? We used that before. What property is that? Or definition or whatever else? Definition of congruent segments. That's true. So now we have that this is congruent to this. We also have this is congruent to this. We also have that the angles are equal. So can we say the two triangles are equal? Yes, because of side, angle, side. Triangle W, Y, Z is congruent to triangle Q, Z, Y, because of side, angle, side. And then what's the last thing we're going to say? This. What lets us say that? No, we use SAS to get the triangles congruent. Because the triangles are congruent, what's true about their parts? What? It's not S something. Congruent parts of congruent triangles are, excuse me, corresponding parts of congruent triangles are congruent. CPCTC. You need to memorize that one. Needs to be in the whole brain hole. I think it's easier if you remember what the words mean, and then you can do CPCTC. But you can do it however you want to do it. But you've got to remember it. Corresponding parts of congruent triangles are congruent. CPCTC. We did it. It's a minor miracle. Let's look at 8. The roller coaster track shown in the photo on page 285 appears to be composed of congruent triangles. On page 285, they got a picture right here. It's a different triangle, different picture. 285. Oh, well, that's done. Why do they waste our time with that side quest? Okay. Congruent triangles, possibly. Portion of the triangle is shown. If QR and ST are perpendicular to QT, etc., 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 prove triangle RQV is congruent to triangle STV. Let's draw our little picture. We've got this shape. Those lines are straight. I said they are. Let's see. QR, we are given that QR, time to retire this marker. It's about had it. Let's see, I guess I should label the letters real quick. Q, R, S, T, and V. QR is perpendicular to ST. And, oh no, just kidding. I didn't read that right at all. Hold on, time out. Let's try again. QR and ST are perpendicular to QT. Triangle VSR is isosceles with base SR, and QT is parallel to SR. We want to prove, I feel like this one's going to be way easier than the last one, but let's find out. Prove that triangle RQV is congruent to triangle STV. So we have these lines here, and this is, of course, this line. We've got a couple of things. All right, so we are given that QR and ST are parallel to QT. QR is not parallel, perpendicular to QT, and ST is also perpendicular. We're given that VSR is isosceles with RS as the base, and we're given that QT is parallel to SR. And we're supposed to prove RQV, so we're looking at this triangle and STV, that triangle. So we already have a side. We can get an angle real easy, so if we can get another side, we're cooking. Well, as long as it's the correct side, because we can't do angle side. That's not a thing. Great. What should we do? I don't know if this one's going to be quite as easy as I thought, but it's not going to be too terribly difficult, I don't think. The fact that those are perpendicular, what does that mean? I drew the angles on there. What are those angles? They are equal because they're right angles, right? And all right angles are equal. So we can add those two. Go ahead and get that those are congruent. Make sure that that's in there. So angle RQV and angle STV are right angles because definition of perpendicular, right? And they're congruent. Angle RQV is congruent to angle STV because all right angles are congruent. Great. That's possibly useful. What else could we do? Since it is isosceles, what can we say about those sides? I marked it, but we should go ahead and say that, right? Not RQ. That's a different triangle, right? RV is congruent to SV. We can go ahead and say that because it's isosceles. You're going back to the given, which is good. That's a perfect thing to think through. So RV is congruent to SV because isosceles, definition of isosceles. Great. It's already marked. So we use this, This gives us all kinds of stuff. The fact that they're isosceles also tells us about another angle too, which we may or may not want to use, but that it does tell us something. What else does it tell us about the isosceles triangle? Q isn't in the isosceles triangle. RVS is this one down here. RVS. Look, we got an isosceles triangle. ABC. What do I know about that triangle? Two of the sides are congruent. That's what isosceles means. Equilaterals, all the sides. What else do I know? I can look at your notes or the book or something. What else do I know about isosceles triangles? What about the bases? Bases are congruent. So in this example, that's down here. This is congruent to that. A is congruent to C. Where's the base of this isosceles triangle? RS. So what angles are congruent? Yeah, there's multiple angles there, right? So how do we name this angle? What we're saying is ultimately that this angle is congruent to that angle, right? How do I name that angle? RQV would be down here. No. This has been true from the beginning. When you name an angle, the middle letter has to be where the angle is. So it's got to be VRS or SRV. So how are we going to name this angle? VRS. So angle VRS is, what am I writing? Congruent to, how would we name that other one? RSV. I'm going to do VSR. It's the same angle, and you are correct. That is it, just to keep our lines the same. But I wouldn't count off for that probably. All right. All right, to angle VSR. Base angles of an isosceles, right? I think the book calls that the isosceles theorem, but whatever. Because I remember take the, like what the theorem is or the name are both fine. Great? All right, so we got that congruent to that. We got that congruent to that. Now what could we do? We didn't use this, right? We didn't use that. We've got all kinds of things. That if we kind of do some of these individually, we've got a couple of parallel lines. We've got RV, right? Got a T over here and a Q and an S. What can we say around this transversal? It is infinite if I extend it. That's true. Not what I'm asking. Which ones are congruent? Is it the same side stuff or is it the alternate side stuff? Alternate side stuff. right? So I could get like this angle is congruent to this angle, right? Which would be good. This is the part of the triangle we're interested in, right? So that could be useful. I could also do the same thing, but for this other one, right? I could do this angle is congruent to, so I could put this one on there, right? So I could say, I've already got this and this are congruent. I could say that this one, this alternate one is congruent because of that. I could say that this alternate one is congruent because of this transversal, right? So angle RVQ is congruent to angle VRS. Look, that matches. That's going to be handy, right? And do the other one as well because it's the same thing. So angle SVT, that's this one. Remember, that's in, so you count it in that order. So SVT would be this angle, right? This one is alternate interior with this one, right? SVT is congruent to angle R, no, we label it with V first, right? VSR. Those match. That's handy mandy, yeah? We just said that this is because of alternate interior angles, right? So we've got this is congruent to this. We've got this is congruent to this. But these two are also congruent to each other, right? So what can we do now? We can say that this one is congruent to this one, right? Right? Because they're also congruent to those. VRS, VSR, and VQ. So we can say RVQ is congruent to SVT. What property lets us do that? It's the A is B and B is C, then A is C again. What's that one called? Transitive. So we've got this side is congruent to this side. We've got this angle is congruent to this angle. We've also got these angles are congruent. So do we have a proof of congruence yet? Yeah, which one? No. Angle, side, angle, side, angle, side, angle, angle, side. I've only got one side, right? But I've got two angles. Angle, angle, side. Triangle RQV is congruent to triangle STV because of angle, angle, side. All right, kids, we're just about out of time. We have Thursday's class and then a test. Does that sound right? Congruence transformations. Yeah, that's what I'm saying. We have one more class on Thursday. Go over congruence transformations, and then we have a test on Tuesday. So see you later.